Today we're looking at 7.1 Part 2. This starts on page 4 of your notes and goes to page 7. We're going to talk about natural logarithms. Logarithms in base E are known as natural logarithms. So you can see it written here. The log base E of u, or whatever we're taking the natural log of. We write that, we write that with the form ln, meaning natural log base b of u. Okay? So it can be written either way. You go on your calculator, you're going to see this button. What is the derivative then of y is equal to the natural log of u? Let's look at this graph for a second. The blue line is log base 10 of x, and you can see it goes through 1, and if x is 100, then 10 to what power equals 100? Well, y equals 2. This is the natural log graph. It looks very similar. So base E. At 100, its answer would be 4 for y. So when we think about the tangent line to this graph, or the derivative, right, we can think of the line maybe something like this. If we're talking at this point, it's going to be a positive slope, right, for this green graph. So if we use what we learned in part 1 of 7.1, here's the logarithm, and I'm going to take a derivative then. The derivative is 1 over u times the log, same base, of e, times by the derivative of whatever u is with respect to x. Now, this part right here, log e of e, well, let's put it in exponential form. E to what power equals e? Well, we know that this equals 1, this whole log. So, our derivative then is simply 1 over u times the derivative of whatever u is. Okay, we're going to do a couple examples using e and the natural log on your calculator, and then we'll get back to finding the derivative of the natural log. Turn the page. You can pause here and attempt to fill these questions in using your calculator and what you know about switching to exponential form of these natural logs. Here's the answers. You can pause it and compare your work. Notice here, in order to test in the calculator, I needed to use the change of base formula. And here, I rewrote the natural log in logarithmic form. I only did that for ease of my understanding. You can leave it in this form if you want. And then in exponential form, it's easy to see e to what power gives me 1. Well, this answer is 0. And you can look at the rest. You can again pause it on the top of page 5 and try to solve for x in these equations, remembering this logarithm and exponential form and how you interact between them. So just to get you started, for number 1, we would write this in exponential form, which is base to this power equals x. Well, I can see that x must be 64, etc. You do the others on your own, and I'll show you the answers in a minute. And here are the answers. Pause it, take a minute to look at each of these steps if you didn't get these same answers. Okay, let's get back to finding the derivative then of the natural log. I've rewritten the rule here in this box. So if y is equal to the natural log of u, then the derivative of y will be 1 divided by u, whatever you're taking a natural log of, multiplied by the derivative of u, whatever this is, with respect to x. Okay, let's have a try. So here we're looking at the derivative of y will be 1 over u, in this case u is 7x, multiplied by the derivative of u, which is 7. And so if I would reduce that, I would get 1 over x. The 7's will cancel out. Looking at number 2. The derivative of y equals 1 over u multiplied by the derivative of u. Well, we know a derivative of the constant will be 0. So that answer is 0. Number 3. Now, I can see that u here, we're going to use the product rule inside there. So let's see, the derivative of y is equal to 1 over u. You know what, before I get started here, I can write that down. What would be easier than using the product rule is to simply multiply this first before we even start the question. Let's do that. So the original question we can rewrite as the natural log of, these are conjugates, it's going to be x squared minus 9. That's a lot easier to take the derivative of that than doing the product rule here. So now we've done 1 over u multiplied by the derivative of u is going to be 2x minus 0. Okay, that was much simpler, and our answer then is 2x over x minus 3. I'm going to leave the factors written out. Good. Looking at the top of page 6, when I look at this question, we can see we're going to need to use the product rule to find the derivative. We've got x to the power of 6 multiplying by this natural log. So that's going to be our f and our g. Okay, so let's consider this. Let's write it on the side. Whoops, not f derivative, just f derivative, g, and g derivative. I'm going to pause and you fill in those. Okay, so I'm sure you could find the derivative of f. That was just the elementary rule of differentiation. G then included the natural log, so when we found the derivative, here's what we're learning today. 1 over u multiplied by the derivative of u, which in this case is just the 3. And that equals 3 over 3x plus 7. Okay, so now the derivative of f, using the product rule here, is going to be the derivative of f multiplied by g plus f multiplied by the derivative of g. Now we know we like to leave our answer with a common factor factored out. So in this first term here and the second term, I can see that the numerators will have a common factor of 3 and 5x's. If I take that out, I will be left with a 2 natural log of 3x plus 7 added with a x over this denominator. Good. Let's look at number 5. Whenever possible, we're going to try to simplify before finding the derivative. It just makes finding the derivative much easier. So let's see what can be done here. We know we can write this fourth root as an exponent. 1 over 4. I see inside here this is a trinomial. Can it be factored? Let's see. Something that multiplies to 1 and adds to negative 2? Yes. It's a binomial square. Let's see here. If you want to write it down, what multiplies to 1 and adds to negative 2, negative 1, and negative 1. So that would be x squared minus 1 squared, and that's still all inside this power of a quarter. Okay, we know the rule of logarithms, so I could multiply this through, I guess. That would work, yes. That would be a, yeah, let's do that. The natural log of x squared minus 1 to the power of, now an exponent onto exponent we multiply, so that would be 2/4. That would be a half. Good. Okay, now the rules of natural logs and logs, we know that this exponent can come as the coefficient. So that looks a lot simpler than what we started with. Now let's take the derivative of that. Okay, we've got the coefficient of a half already, so that's going to be there. Now we know the derivative of is 1 over u, so we've got 1 over, now this 2 is in the denominator still, we have to keep the coefficient, x squared minus 1, that's the u, multiplied by the derivative of u, which is simply 2x. Now we're going to see the 2's will reduce, and our derivative is x over x squared minus 1. I guess this is a difference of squares. We could leave it also like this, which would also be a good answer. In number 6, we see we can simplify simply by multiplying the x cubed throughout. We could also use the product rule here inside, but this is easier. So the derivative of y is going to equal 1 over u, which in this case is x to the power of 5 minus 6x cubed, multiplied by the derivative of u, which is 5x to the power of 5 minus 1, is 4 minus 18x to the power of 2. Okay, let's see if this can be reduced at all. In the numerator, we're going to have just 1 times this. I'm going to factor out a common factor of x squared. So I'll be left with a 5x squared minus 18. And in the denominator, I see I've got a common x cubed, which would leave me with an x squared minus 6. Okay, we can reduce some x's here, and our final answer will be 5x squared minus 18 all over x times x squared minus 6. Looks good. Can number 7 be simplified at all before we take the derivative? I don't see any way that this can be reduced or simplified. Okay, so let's do that. We've got the derivative of y is going to equal, now we've got the coefficient 3, that stays here in the numerator, and it's going to be 1 over, 3 times 1 will just be 3, 1 over x to the 4th all over x minus 2. Now remember when we did this the first time, it's 3 divided by x to the 4th over x minus 2. When we divide fractions, we reciprocate and multiply, so this is 3 times x minus 2 over x to the power of 4. I'm just going to write that in the next step. 3x minus 2 over x to the power of 4. Okay, multiplied by now the derivative of u. We can see we're going to use the quotient rule here. I am going to pause, and you are going to write f and g in their primes. Alright, I cleaned this up a bit. I moved this over so we could fit it. Okay, so now the quotient rule, finding the derivative of u. We've got f factorial, sorry, f prime, not factorial, multiplied by g, subtract f, multiplied by g prime, that's nice, all divided by g squared. Okay, this is nice. I can see that this will reduce somehow. Okay, let's simplify this. I can see x minus 2 will cancel with one of these. I can see some x's will cancel out here, but let's take out a common factor first. Okay, so we've got the 3, and then within those square brackets, we're going to have, if I multiplied it out, 4x to the power of 4 minus 8x cubed minus x to the 4th, all over x to the 4th times the 1x minus 2. Okay, now let's take a common factor out of that numerator. Go to 3 x cubed. We'll leave 4x. Oh, I could have combined those like terms. Shoot. Oh well. 4x minus 8 minus x all over x4, x minus 2. We'll do that next. Okay, so there's 3 x's here, 4 on the bottom. Those will cancel, 1 will be left on the bottom. And last but not least, we're going to have 3, 4x minus 1x, 3x minus 8 over x, x minus 2, our reduced derivative. To be clear again, what does derivative mean, or what does this what's the point of this? If we were to graph this function, we want to find the slope at a point on that line. We know that it's the slope of the tangent line at any of these points is given by this equation. So if they gave me a point on this graph, you know, at maybe negative 6, 2 was on this graph, I could put the 6 in here and find the tiltedness of that graph at this point. Okay. It's the rate of change, the change in y's with respect to the change